Hi, welcome to the Monday, November 1st edition of Period 7 and Period 8 Earth Science. I'll be your host, Jesse Stonewood, sort of going to be your host for the next 80 minutes of my life and your life. I hope you had a nice break, and and I hope, I don't know, just hope you're having a nice time. Good day. All right. So, a couple things to start off. One is all of the tests are graded, all of the grades are updated in PowerSchool, and I'm obviously not there to talk about all that. So, we are going to go over those things on Wednesday. Like today, we're just going to start the next chapter. The next thing is that you should have the A1 notes, which says measuring the motion of lithospheric plates. You should have a set of orange notes in front of you. We're going to just get right into it. The first thing that we'll do is go over these notes. And then there's actually a second set of notes as well. And then hopefully you'll have time to get the lab done today, A1 lab. So without further ado, let's get rolling. Okay. So I'm sure that you've heard by now that there are different layers of the Earth, like the core and the mantle and the crust. We are going to be looking at the crust of the Earth, so like the outermost layers. So maybe don't write anything for a second and just hear me out. So I don't know, maybe a month or month and a half ago, I talked about the Earth being like a bowling ball covered in Vaseline and then covered in like a chocolate coating that hardens, like the ice cream shell kind of stuff. And so I'm gonna refer to that a bunch of times. So that model is good in some ways and really bad in other ways. But keep that in mind. You got a hard chocolate covered, Vaseline covered bowling ball in your mind as to what the Earth looks like. So the hard chocolate part that breaks up into different chunks, now we can start writing all this stuff about the crust. The hard chocolate part is the crust, the thin outermost layer. There are lots of different types of crust, but kind of like two basic categories. Number one is continental, and number two is oceanic crust. Little compare and contrast going on here. So oceanic crust is more dense, around 5 to 10,000 meter sticks thick, and whereas continental crust is quite a bit less dense and thicker. Like it's just a way bigger depth, the continental crust, so 30,000 to 50,000 kilometers thick. The oceanic crust, like some of it's being made like right now. It's like a baby. And then it's also like way more simple in structure. So if you remember what basalt looks like from last chapter, it's like this dark rock. There's you can't really see any sort of like crystal-y patterns in there. They're very tiny if you can see them. Whereas oceanic crust is way more complicated, so a much wider variety of rocks and minerals, much different topography, and it's quite a bit older as well. So it's kind of like we have these, like, if you're going to the bowling ball analogy, we have like thicker and thinner chocolate plates. The thicker ones would be the continental crust, and the thinner, more dense ones would be the oceanic crust. And then let's do just some side notes here. So I'm sure you've heard before that we can kind of divide the Earth up into these three basic layers. The core, come on now, here we go. Come on, iPad pen, you have one job. You can do this. I believe in you. All right, let's see if this works. Okay, yay. Okay, we've got the three basic layers, the core, the mantle, and the crust. But how do we differentiate those? Why do we have these three layers? And this is really based on the chemistry. So rocks and minerals. So the crust has silicates and other rocks and minerals that are quite different than mantle. The mantle, which is primarily a rock called peridotite, and then the core is more like iron and nickel. But we can also divide the Earth's layers up based on density or state, and by state I mean solid, liquid, or gas. And if we do that, we end up with a kind of different set of categories. So we have the inner core, we have the outer core, We have what we call the asthenosphere and the lithosphere. And so this kind of like bowling ball analogy sort of makes sense here, but the inner core is solid, the outer core is liquid, and then the asthenosphere is what we call plastic, which is part solid, part liquid. So that's really the Vaseline type layer. Now, I'm not saying that the asthenosphere is made of Vaseline. What I'm saying is that there's a layer of the earth that has a consistency kind of like silly putty or Vaseline, and that's because it's like partially melted. It's not melted all the way to where it'd be liquid, but it's not solid either. And so we should talk about the word plastic too, because when you hear the word plastic, you probably think about like plastic bottles or like plastic toys or something like that. And so that like it's a material. But plasticity really also refers to whether or not something, it's like a characteristic, like whether or not something can be molded and deformed and changed into different shapes. And part of the very useful, one very useful property of plastics is that they are plastic, because you can melt them down and form them into lots of different shapes. So it's probably a different use of the word plastic than you have seen before, but it is an important one for us here in earth science. And then the lithosphere is solid. And so I don't care what you say, the earth is a three-dimensional round object. And so that's why we get like sphere, like the atmosphere and the biosphere. Here we have the asthenosphere and the lithosphere. And then lith means rock. So we have like the solid part of the planet, like the outermost crust. So that's like our different, make sure that you've written down these side notes, and again, pause the video if you need to catch up there. So again, we can separate the Earth's layers based on the types of rocks and minerals, and we get core, mantle, and crust. Or we can separate the Earth's layers based on like their densities, and in which case we get these different kind of categories here: inner core, outer core, asthenosphere, and lithosphere. And let's be really clear here, because a lot of times students miss this. What we're talking about here is that this outer portion of the Earth is rigid. That's the solid part. That's the lithosphere. And the lithosphere rides on this more plastic, partially melted layer called the asthenosphere. It's not that the mantle is partially melted, because the upper part of the mantle is solid and it's part of the lithosphere. And if that is hard to remember, so you could think of it like this, like the lithosphere equals the crust plus upper mantle, whereas the asthenosphere is like the partially melted part of the mantle. Again, the upper mantle and the asthenosphere are made of like very similar rocks and minerals. It's just that they're at different depths, different temperatures, different pressures, and therefore different like densities. So, all right. And then over here, we've got the crust divided up into oceanic and continental crust, and then the mantle. So again, if we go crust, mantle, core, it's based on chemistry. If we go inner core, outer core, asthenosphere, lithosphere, it's based on density. One other important thing to note is if you look at this is really easy to miss, but if you look at the scale here, side to side on the x-axis, we have 500 kilometers. But Y to the sky right here, we only have 50 kilometers. And so we have like a different horizontal scale than we do a vertical scale on this diagram. And the reason why is that the crust and the lithosphere is just really, really thin compared to the mantle. If you think of the Earth as a giant apple, the lithosphere is like thinner than the skin of the apple proportionally. And so diagrams like this have to be vertically distorted to even show the lithosphere, to even show the oceanic and continental crust. If we had like the same scale, like 500 and 500 right there, then we really wouldn't be able to see the features of the lithosphere because they're just way thin compared to how deep the mantle is. Beneath the crust is the mantle, which is very different from the crust in terms of its chemistry. Like I mentioned before, it's primarily made of this material called peridotite, and we will look at that in a following chapter in Earth Science. The upper part of the mantle is rigid, and that upper mantle plus the crust is what we call the lithosphere. And then down below, beneath the lithosphere, is what we call the asthenosphere. I don't know if it's like Greek or Latin or some other language where we get that prefix astheno, but that means plastic. And not like plastic toys, but plastic like it's easily distorted and bent and changed into different shapes. So, all right, so now it's 2021 and I'm telling you some stuff and you're like, okay, that's cool. But how do we actually know that this is true? Like, how do we actually know that the Earth is divided up into these different plates, these different lithospheric plates? How do we know that the lithosphere is riding on top of the asthenosphere? How do we know where it's moving, what direction it's moving, how fast it's moving? How do we know anything about this? Let's go back in time to the mid-1950s, actually all of human history until the mid-1950s. And I know that you're going to be just writing down the red words and hopefully not turning your brains off after that. But like, let's go to here first and let's pretend that it's like in the 1950s and you are on a boat and you're in the middle of the ocean and here is your boat. It's a sailboat. It's very sophisticated. That's why I drew it very sophisticatedly. Anyway, there you are. You're a scientist. And over here is like Africa and Europe. Again, we're in the middle of the Atlantic Ocean. And over here is going to be like South America and North America. And you are on a boat in the middle of the ocean. And on your boat, you have a couple of things that you can do. Number one, you can send down these fancy signals and you can measure the magnetism of the rocks beneath the ocean floor. And then the other thing that you can do is you can like collect rocks from the ocean floor and examine them. So one weird thing that scientists discovered is that the magnetism of the rocks of the ocean floor had a weird pattern, had a strange pattern. So as you're going from the center of the Atlantic Ocean over towards Europe and Asia, they found that the magnetism of the rocks pointed in one direction, and then that direction flipped. Now, what are we talking about, the magnetism of the rocks? So what we're talking about here is when basalt, which again is a dark rock, it is low in silica, it is high in iron and magnesium. It's a dark rock that has a lot of iron containing minerals, and those minerals line up with the Earth's magnetic field as they cool. So you can basically kind of get like a little magnetic time capsule in each rock. And if you know where the rock was and you can keep its orientation straight when you collect it, and you can measure the magnetism of that rock, then you can see, okay, the Earth's magnetic field was lined up in one direction at the time that rock was made. What's weird, though, is that the minerals found in the next band over as you're going towards Europe and Africa, those minerals line up in the opposite direction. And then they flip again. And then they flip again. And then they flip even more. And what's even stranger is, let's say you get back in your boat, you're in the middle of the Atlantic Ocean, and you are starting to cruise over towards North America and South America. You see the exact same pattern of magnetic reversals, but in the opposite direction. So it's the exact same pattern, but now you're going towards the North America and South America. And so we see these magnetic reversals. We see a definite pattern, and then we see like a mirror image of that pattern depending on what direction that you're traveling in. Another thing that you can do in your boat is you can pull up rocks and you can take them back to your laboratory and you can get an estimate for how old those rocks are. And what they found was that the oldest rocks are towards the continents, and the youngest rocks are right in the middle of the ocean. And this puzzled scientists for like quite a while, because you have to remember, you're on your boat, you're in the middle of the Atlantic Ocean, it's like the 1950s. You don't know about plate tectonics. You don't know that the Earth is divided up into these different lithospheric plates, and the lithospheric plates are riding on this plastic mantle. You haven't been filled with the wisdom of your teacher telling you that the Earth is like a giant Vaseline and chocolate-covered bowling ball. You don't know any of that stuff. All you know is you see these weird magnetic reversals, you see older rocks towards the continents and younger rocks towards the center of the ocean. What the heck is going on here? All of this information, these weird different phenomena, led to this theory of seafloor spreading. And the theory of seafloor spreading is basically what is still the accepted kind of wisdom of scientists at this point. So it explains how the Earth's magnetic, it explains the variation in magnetic field or magnetic field striping. It also explains how the age of rock increases as you go from the center of the ocean, or that's what we call a spreading ridge, towards the margins by the continents. So let's take a look at this. So what we're talking about here is magma rising up through these spreading ridges. We find the youngest rocks towards the center, and then the oldest rocks towards the margins. And it kind of creates this like geologic conveyor belt where this is called a spreading ridge, and the plates move out. These giant tectonic forces move these plates away from the spreading ridge. We're going to watch some videos. I queued them all up. Hopefully they all work. But these are like amazing features. So volcanoes taller than Mount Everest, canyons deeper than the Grand Canyon. Most volcanoes, most volcanic activity on planet Earth takes place along these spreading ridges. And up until recently, we have never even witnessed any of it. It's like this huge undiscovered, unexplored part of our planet deep beneath the ocean floor. These spreading ridges, we now have mapped them out, and they kind of look like gnarled kind of seams on a baseball, basically. So they each have different names, and we have one right off the coast of Oregon called the Juan de Fuca Ridge. Again, this is where the plates are spreading apart. There's another view, the Juan de Fuca Ridge, East Pacific Rise, the East Antarctic Ridge. So again, these kind of puzzle pieces that are moving apart from one another at these spreading ridges. This is a very pixely version of this, but it's the best one I could find on short notice, and I wanted to point this out. So we have a general, like here we're in the middle of the Atlantic Ocean, a general north to south kind of direction. But then we have these huge breaks or fractures that are lateral right there, and that is what we call offsets. That's where those plates shear apart from one another, kind of perpendicular to what we say perpendicular to the axis of the spreading ridge. This is a north-south axis, and the offsets are east-west. All right, let's go on with the rest of the notes. And I'm sorry I can't be there to answer all your questions. And so make sure that your phones are put away. Make sure that they're in your backpacks. Make sure that you're paying attention and writing all the words down. And then make sure you're pausing the video if you need to catch up. The ridges spread at different rates. So you can see from there, the Arctic Ridge is spreading much more slowly than the East Pacific Ridge or the East Pacific Rise. And then the last part is that basically like these ridges kind of like encircle the globe like seams on a baseball, on a crazy looking baseball. And that, but it's not like these, that they're super smooth. They're kind of jagged where those plates shear apart laterally. And those are called the offsets. All right. Excuse me. Okay. How do we know? How do we know how fast they're moving? How do we know what direction they're moving? How do we know if they're moving up or down? It's all about GPS, or Global Positioning System. So now, and this is a tool that we have available to us now. Back, 50, 100 years ago, we definitely did not have the GPS system in place. In fact, GPS was developed by the Department of Defense in 1973, or at least that's when they said they started doing it. They probably started doing it before because it's like crazy alien technology. I'm just kidding. I don't know anything about that. But 1993 is when the system came online, and it's 24 satellites that orbit the Earth at a height of around 20,000 kilometers, or 20,000 meter sticks above your heads right now. That is an elevation that allows these satellites to like move with very negligible air resistance, so they can just like zip around the Earth in this geosynchronous orbit. But it is not so far as not so high above the ground that they would like lose they would escape because of gravity. So it's like the perfect height for them. And then we have receivers, on stationary receivers on planet Earth. And these signals are bouncing back and forth between the GPS satellites and these receivers at all time, 24/7, 365. Because of that, we can measure distortions in those signals, and then we can get whether the receivers are moving horizontally, and by that I mean like what direction, north, south, east, or west, or whether they're moving vertically and changing in elevation. And they're super sensitive. We can detect to within like several millimeters. That's what we're going to talk about in the next set of notes here. GPS stations have existed for around 3 decades. So yeah, it's not just over a decade, it's around 3 decades. So in the grand scheme of things, a relatively new technology, but in the scheme of like your life and my life, it's actually a little bit of an older technology. So global positioning systems is what we're going to talk about in the next set of notes. Hope you got all that. Thank you for your time and attention on that one. And yeah, bye.